stage is yours.
Thank you so much. I'm Juraj. I work at the image processing department at Fraunhofer, and I work in the virtual inspection group. So what we do is we do inspection, but in the synthetic domain, in a virtual domain. And today I would like to talk about some prospects that deep learning can use by using synthetic data for the surface inspection in this case. So there are several challenges when we want to automate visual inspection. So we specifically focus on metals because they have high reflectivity, they are highly problematic, industry doesn't know how to handle them properly. And metals, depending on how they were produced, depending on what their functionality is, they can have different kind of surfaces that have very interesting patterns. The problem is if you want to automate something, these patterns produce false positives, and this introduces problems. Another problem is depending on what kind of product you have, what kind of needs you have from the product, what kind of quality levels you expect. You have to tailor the inspection specification to your specific needs. So it depends on the object geometry, on the type of defects, how strong the defects are, and similar. There is also a diversity of defects. So we have defects that are geometrical, defects that are purely surface-based, like some sort of impurities, or we have simple stickers. The question is which ones are defects, which are not, which should be ignored. This is again up to the specification, but our recognition models need to handle all of those nonetheless. And yeah, once we start developing the recognition models, we run into a lot of more trouble as we go along. So when we try to automate, we basically have kind of two scenarios. So we either have a small data set at our hand or we have a big data set. Here we actually assume that the inspection setup is already made and we can actually collect some data from it. This is like down the line, up the line from us. So yeah, so a common thing is we have a small data set, and if you are very lucky, you are in a common domain, so you can find some additional data, you can collect a huge data set, train your model on that, and then just fine-tune it on the target data, and this usually works pretty nicely. But sadly, more commonly, you are in an isolated domain, you're working on something highly specific, highly new, and there is no other way than to use the handcrafted methods. At our department, we actually have tools for that as well, so we have some experience with those projects as well. But when we are talking about large data sets, we usually talk about supervised learning. So you have a lot of samples that are clean, correct, and you have a bunch of defected samples, and then you just train a recognition model on that. You separate the good from the bad, and this usually works if you have enough data. If you have a lot of data, you can probably also collect more. But we are more interested in the scenario which is industrially more interesting because defects are rare. Defects are hard to acquire, especially the hard defects that are highly dangerous. So usually we have an abundance of only okay samples, so only correct products. And then what we do is basically we just train the model to learn what is okay and ignore the rest, or report the rest. And for the purpose of this talk, I will focus on this, although we actually, as you will see later, we can also handle the isolated domain. So arguably the most popular algorithm for anomaly detection is patchcore. It is relatively new, and it is quite cool because it only learns what is okay. You only give it the data so that it knows what it should learn to ignore, and then everything else is reported as an anomaly. And the cool thing is that you can reuse pre-trained models, so not a lot of training is required, and everything is fun and games until you start running it on large data sets and large images, and then it's game over. So it has a really high memory consumption. A lot of industry colleagues were complaining about that. And basically it restricts you to either using small data sets or using small image sizes. So if you have a huge image, you patch it up into small areas, and then you train like multiple recognition models for each of the areas separately. So what we presented last week on ECCV was a sequential version of the patchcore. We just inverted the algorithm. So we just use the memory that we require at the moment, and we update the model just as a usual recognition model. And what we could basically apply it to is large image sizes and on running it also on consumer hardware. So I was actually running it on a small laptop as well. And additional benefits, what we could use was we could actually train these models like in parallel on different parts of the data sets, train them to collect the knowledge. And then because of our inversion algorithm, we actually can design a really fast transfer learning method, which we call core set melding, which just uses the core sets and melds them together, so you combine the knowledge in a highly explicit way. So this is like a common way that we talk about deep learning. So we focus on the model, and we know that feature extractors are important, because if you extract good features, the recognition is easy. You just draw the line and it kind of works. And this is common for a model-centric view. So you focus on the model, and if you can control it, you can control the performance on the recognition task or whatever you want to apply it on. However, the problem is that when we talk about good features, we are subjective, because good features are dependent on the task that we apply it on, and it's not so reusable. It's not completely reusable. But some features are generic enough, so like simple edge detection or some contour recognition or highlighting, so some things can be reused. And this is kind of why these methods actually work with ImageNet pre-trained models. So there are general features, but there are features lacking. And the most important part in the whole story that is often being ignored is actually that the data is the stuff that we train our models on, and the data is actually influencing it a lot. So the data-centric view is where we say, okay, control the data and you will control your model and thus the overall performance. And some examples how you control the data, well, you target the weaknesses in your data sets. So you have usually an imbalance between defect types. So we have an abundance of okay samples usually, and defects are quite much rarer. And some defects are so rare that you maybe have like 1 or 2 samples of them in a data set of 100, for instance. You also have to learn to ignore a background. So once you deploy a model in a factory, what is oftentimes a problem for recognition systems is there is a cloud coming on, so the lighting changes on the day of the year. You have people walking, producing shadows. You have objects that the products are placed on. They have wear and tear as well, and they can also confuse the model, so they need to be ignored as well, and you have to handle it somehow, right? Another problem is that you have misalignment. So if you have perfect alignment, that's good. Usually this is quite expensive. So you want to focus more on more robust algorithms and recognition systems that don't care about small misalignments and still works quite well. And we also have contaminations. So this is stuff that happens to be on the surfaces of the objects. So the simplest thing is like a dust bunny. So it's just like a piece of fabric that falls onto the object, or dust, or quite often we also have soap residue and water stains on them, or droplets of water and oil, quite common ones. But the problem is, how do we target these weaknesses? Because we just said before that it's hard to acquire this kind of samples. So we have kind of 2 questions. So how do we even acquire enough of these rare samples to target these weaknesses in a data-centric view? And how do we even acquire the edge cases, which are so rare that are you know they are theoretically possible and they are really dangerous, but you have no idea how to produce them. So collecting the data is quite expensive. Like if a defect happens once in 10 years, then yeah, that's quite expensive to train a robust model. If you want to do a data augmentation, you can do it. It helps. We proved it also, but the data augmentation is limited. You can only do certain stuff in the image space. If you have certain misalignments that are so radical that the reflection of the surface changes, you cannot do data augmentation there. You have to use the 3D domain. And generative models are quite popular. They do help. So if you train a model, if you have enough data to train a generative model or fine-tune it from something pre-trained, it helps. But the problem is it produces hallucinations, and this is proven on and on again. And the second problem is, how do you generate out-of-distribution samples? So if something is so rare that the model sometimes can generalize to it, but can you really adjust it to your specific needs? From the current papers, it is really hard to find a model that can really do that. And one of the major problems is also that there is not enough industrial data out there to actually train a decent foundation model for generative models. So we are kind of stuck between these choices. Well, we actually found another solution, much older, all the way back to the 90s and 80s. So we use rule-based synthetic data, which is another way to say that we use something that uses computer graphics and rendering. So when I say rule-based, rules are actually just physical models that we use to reconstruct the reality that we see around us. So like the surface textures, the geometry of the object, the reflectivity and the simulation of light. These are all kind of models of reality that you simulate to ensure that your data will be clean. And another thing that we found out was it actually helps you to experiment quite precisely. So you can just change a single variable, keeping all of them rest, and see how it affects the model. So you can effectively learn what works and what doesn't. And when I talk about the control that you can have, well, you can have a control of the geometry. So we start basically from a CAD file or any kind of geometry representation. And you can also embed like geometric defects on those. You can add product variations quite easily and produce multiple data in this way. You can control it to your liking. We can also model the texture, so we can apply different kind of textures that have physically correct reflectivity patterns. And we can also control the environment, so like what is around the camera, is there some light leaking from the sides, where do we position which equipment, which cameras do we use, what are the parameters. We have control over everything, and we can change them one by one. So there are quite a lot of benefits to using this synthetic data. One of them that is quite staggering is that it is highly reusable and adaptable. So last year we published a dataset on a metallic clutch where we applied our models to a curved surface, and this year we just adapted basically the same model to a flat surface, just tweaking parameters so it matches the machining process of those models. We can generate following a tight specification because computer graphics is actually kind of notorious for being too perfect. So if you have a really tight specification, we can generate it. We can generate variations up to your specifications. So if you need to handle a certain like number of millimeters offsets, we can generate this without problems. We have effectively infinite variability because we use procedural modeling, which is a fancy way to say that we model everything with functions. And we can generate an abundance of very unique samples very quickly. We also have infinite resolution, although a small disclaimer here. So you have the resolution as much as you invest. So as deep as you want to scan into the surface, as much as we can model, right? We are covering edge cases because if you have a theoretical edge case that is really hard to like deliberately produce, or you haven't caught it so far in the production, but you know this could be a serious problem, we can generate it. Because we use everything explicitly, we just use regular 3D modeling or whatever kind of method you want. It is quite explicit, you have direct control over everything, and you can use it directly. And quite important for the industry that we found out was we have consistent quality, so there are no hallucinations in our models. The models are a replica of the reality, and they produce, so we fit them and we develop them by observing microscopy data or just macroscopic data, and we can tweak the parameters to make it look more correctly, but the physical model is the reconstruction of the manufacturing process itself. However, as it is with synthetic data, we do have domain gap that is present because our models are just models of the reality. It's not the whole thing. So we cannot model some maybe higher frequency details or some specific stuff. But so far, what we saw is just simple fine-tuning works pretty well. We tried different kind of domain adaptation methods as well, but fine-tuning was by far the easiest and the best one in the field. Thank you for listening. If you want to learn more, you can check out our project website. We have also different kind of, we work on different stuff. We also work in the volumetrics as well. If you want to, if you have a special use case that you think we cannot handle, we would be really happy to listen to you and see if we can do something about it. And if you want to track some following research that will come in the next couple of months, maybe, you can also follow me on ORCID. And yes, thank you for listening.